Hello friends, let's start our discussion about hydrogen bonding. So the definition of hydrogen bonding is the force of attraction between positively charged hydrogen atom of one molecule and the negatively charged fluorine or oxygen or nitrogen of another molecule is called hydrogen bonding. Okay friends, we know that according to the definition of the hydrogen bonding that hydrogen, nitrogen, oxygen and the fluorine are involved in the hydrogen bonding. And the simple rule of the hydrogen bonding is that the hydrogen already covalently bonded with a fluorine can make a hydrogen bond with the lone pair of fluorine, with the lone pair of the oxygen or with the lone pair of the nitrogen. Second is that the hydrogen that is already covalently bonded with oxygen can make a hydrogen bond with the lone pair of the fluorine, with the lone pair of oxygen or with the lone pair of the nitrogen. Whereas the hydrogen that is already covalently bonded with the nitrogen can make a hydrogen bond with the lone pair of the fluorine, with the lone pair of oxygen or with the lone pair of the nitrogen. Here this dotted line shows the hydrogen bonding. So the examples of the hydrogen bonding from our daily life are water as the most common example, honey, paints or glue, protein, soap and detergents that we are using, and the DNA. Now let's discuss the hydrogen bonding in a water molecule. Now look at the structure of the water molecule. Here it having a two lone pair and two bond pair of electrons. Water molecule can easily make 4 hydrogen bonds with other 4 water molecules. Now look at here in a diagram the central water molecule making 4 hydrogen bonds. The red dotted line shows the hydrogen bonding. Here the central oxygen having 2 lone pair of electrons in a water molecule can easily make a 2 hydrogen bonds with other 2 water molecules. On the other hand, the central atoms, the hydrogens can also make a hydrogen bond with other two oxygens of the other water molecules. And in this way, the central water molecule can easily make 4 hydrogen bonds. Therefore, the hydrogen bond in a water molecule is very strong and is a perfect example of hydrogen bonding. Now let's talk about the hydrogen bonding in hydrogen fluoride. Now look at here the structure of the hydrogen fluoride. Here it's having 3 lone pair of electrons and 1 hydrogen atom. Therefore, the hydrogen bonding in hydrogen fluoride is weaker than that of water. We know that the halogens are the strong acid. Then why the hydrogen fluoride is a weak acid in the halogen series? So the answer is that the hydrogen bonding in hydrogen fluoride makes the molecule difficult to donate proton. Therefore, the hydrogen fluoride is a weak acid. Now look at here in a diagram. Here the hydrogen is embedded between the two fluorine atoms. Therefore, it's become difficult for the hydrogen to go away from here to donate a proton. Friends, we do washing on the daily basis. But do you know that the hydrogen bonding is involved in our cleaning action? So, the soap and detergents also do the hydrogen bonding. Soap having two poles that are polar head and the non-polar tail. Look at here the soap molecule. This soap molecule having a polar head and a non-polar tail. And according to like dissolve like. So the polar head dissolves the water that is polar in nature through the hydrogen bonding, whereas the non-polar tail entraps the oil, grease or dirt because these are non-polar in nature. As a result, the cleaning of cloths takes place.
In this video, we'll talk about hydrogen bonding and how it takes place and really try to give you a visual picture of what's going on there. So we have a water molecule here. We have the red is oxygen and the white are hydrogens. We have H2, then the oxygen, H2O. When we look at a water molecule, it is a polar molecule. That means that one side has a positive charge and the other has kind of a negative charge. We call it a dipole. In this case, oxygen's more electronegative than the hydrogens. So this is going to be the negative side, and this is going to be the positive side. It's polar, it has poles. If we look at the surface of the water molecule, kind of a force field extending around it, because of that difference in electronegativity, we have our negative pole up here and our positive pole around here. This gives us this idea that the water molecule kind of has sides to it. That's really important. Let's take a look at how that plays out with just two water molecules. So we have these two water molecules and they're kind of frozen in space here. And we want to see how they behave in an actual sample of water. So we're going to let the computer simulate that. First, I'm going to optimize the model so it lines them up. We do that. We have a hydrogen bond here. Next, I'm going to set the temperature. Let's set up a simulation and let's leave it right around room temperature. And now this is what we kind of think of as how water molecules are behaving in a sample of water at room temperature. Kind of crazy. They're moving around, they're spinning, and that's just the energy that's in the water there from the heat around. And they do stay together though. This hydrogen bond, it's breaking and reforming, but it stays consistent and holds them together. Every once in a while they start to move apart like they might evaporate, but it keeps them together. Let's turn the temperature up and see what happens. So now I'm going to take it up to about the same temperature as a Bunsen burner. That's a lot more energy. Remember, hydrogen bonds aren't really that strong. Compared to the oxygen and the hydrogen bond, covalent bond here, a hydrogen bond's pretty weak. Let's take it up to about 800. That's a Bunsen burner. And you can see that when we've done that, there's a look, there they go. They just can't stay together. There's too much energy. In essence, you could think of that sample of water, that very small 2-molecule sample of water, is either evaporating or turning to steam. Let's take a look at more water molecules, though, and see what happens. So here's a sample of a bunch of water molecules, and I'm going to put the hydrogen bonds in. And you can see how those hydrogen bonds, they form that network that really holds the water together. If we're thinking of a glass of water, this would be throughout the entire sample. Next, let's give us some energy here. Let's take and put it right about room temperature and see what happens. So there they are. These are our water molecules, and they're all kind of holding together. If you look at any one water molecule, you'll see that the hydrogen bonds are breaking and forming, but they do stay kind of attached together. When we think about the properties of water, it's cohesive, there's surface tension, it has a higher boiling point than similar liquids that don't have hydrogen bonding. The hydrogen bonding has a lot to do with how water behaves. Let's heat this up, see what happens. Let's take it up to that 800 degrees again. There we go. And you can see that when we do that, at 800 degrees, water is going to turn to steam. Those hydrogen bonds just aren't strong enough to hold it together, and it spreads out and forms a gas. So one interesting thing that happens because of hydrogen bonds, when we have water that is frozen, it takes a regular pattern. These are crystals, and a lot of that has to do with our hydrogen bonds here and how the water molecules are lining up so the positive and negative sides can be pointing at each other. So you see the hydrogen bonds here in our crystal of water. This would be moving a little bit as well. These molecules would be moving around some. A lot slower though, because there's not as much energy there. This is Dr. B. I hope this video has helped you kind of visualize those hydrogen bonds, that they aren't quite as strong as ionic or covalent, but they're very important bonds, give a lot of properties to water and to other compounds that exhibit hydrogen bonding. Thanks for watching.